Good afternoon. Welcome to the Bureau of Economic Geology's Austin Earth Science ZOOMERAMA. I'm Linda Ruiz McCall, the Bureau's Information Geologist and Resource Center Manager. For those of you watching live, our rules for using Zoom are such that we're unable to use the built-in chat features, but if you have questions, you can email them to zoomerama@beg.utexas.edu, and we'll answer them at the end of the presentation. Before we get started, I'd like to take a few minutes to thank our sponsors, Austin Geological Society, and John, our speaker today, is here representing them, and Equinor. Today's speaker is from the Austin Geological Society, John Berry. John has worked in exploration for copper, cobalt, uranium, gold, petroleum, and as he says, unromantic things like limestone and water, although I think those are great, John. He has worked on 5 continents in all 7 seas and visited over 60 countries. Today, John will explain why a knowledge of the Earth and what it can provide and cannot provide is going to be essential for survival of our civilization going forward. He'll focus on what geologists can do to help civilization survive in his talk titled, See the World, Save the World, Be a Geologist. And now, John, I'll turn the floor over to you. Thank you very much for joining us.
Thank you, Linda. So welcome everybody. And I hope that you have a really intellectually thrilling Earth Science Week this year. My talk is entitled, See the World, Save the World, Become a Geologist. And I thank Linda for that wonderful introduction. So, what is the need for geologists? Well, as this baby shows, this is a cartoon put out every year by the Minerals Information Institute. Every American born this year in their lifetime will need 14,000 pounds of phosphate rock. That's 7 tons. That is used to fertilize the fields to make sure that we can grow the food we need. This baby will use 75,000 gallons of petroleum in its life for transport and for making plastics and things like that. It will use a half a ton of copper, 10 tons of iron ore. Remember, there's 2,000 pounds in a ton. It'll use a ton of bauxite, and so on, including 330,000 pounds, that's 165 tons of coal, and 27 tons of cement. The whole thing amounts to 1,600 tons per person per lifetime. What we call civilization is totally dependent on this massive use of energy and minerals. But it is utterly unsustainable. Before we move on to why it's unsustainable, here's a British view of this baby that is it's using the same data but for a different year, and it's much more dramatic, showing him on top, or it on top of this huge pile of natural materials. So unsustainability. Ecologists have this concept of carrying capacity. That is the number of any species of animal that a given area of land can support without the destruction of the land and its vegetation and its soil. And if we look at what the human species is presently using, we're using 1.7 Earth's worth of the land's of the resources that the land can yield. That is 1.7 times what the entire Earth can supply without getting degraded. And what this graph shows is that by the year 2050, we'll need 3 times what the Earth can supply at the rate we're going. A man called Schindler said about a decade ago, he pointed out that few in the sustainability movement are willing to admit that achieving sustainability is difficult and maybe impossible without big changes in the way the world operates. And I agree with Schindler absolutely on this. The small things that we're trying to do really are not nearly enough. And that's shown perhaps in this graph, which shows that here in the USA, we're not using 1.7 Earth's worth of stuff. We're using 5 times what the Earth can supply. Europeans are using about 3 times what the Earth supplied, the Chinese twice, the Indians just under what the Earth can supply per person. And this, I'm sure there's an error here, and they meant to say that the people in Niger only use about 1/10 of what the Earth can supply. And what will immediately come to your minds is that, well, these people in India and Niger really don't have very good lives by our standards. They're very poor and they don't have much. But we have to get down to their level of consumption somehow and maintain our standards of living. And that is where the difficulty lies and the near impossibility lies. We have to do things radically different in order to have good lives and live within the Earth's means. Here's what the way we lived before we used all these minerals and fossil energy to make our lives better. This is my office being built in Zambia when I worked there. And it consists entirely of sticks stuck in the ground, plastered with mud, and covered with a thatch of straw. And here's the chicken house that somebody built, built the same way on stilts to keep the snakes from eating all the eggs and the chickens. So while we're moving towards this sustainable future that we hope we can learn to achieve, we have to continue to find all these minerals and fuels that sustain us. We have to continue and do even better at cleaning up the messes left by the mining, the processing, and the consumption of all this material. And both these tasks are performed by geologists to the greatest degree. In addition to that, the amount of stuff mined doubles every 23 years. So by the time that you are in your late 30s, there will be twice as much stuff to be found that needs to be found, and twice as much stuff that needs to be cleaned up. So we will need at least twice as many geologists, probably more, because the task is going to get more difficult. And here this graph shows the way our civilization is progressing. Every year we use a bit more biomass, that's food and forest products. We use a whole lot more construction materials, concrete and reinforcing steel and glass and so on. We use a lot more energy every year, and we use a lot more mined ores and industrial materials. And as you can see, that graph, it's exponential. That graph is beginning to go up very steeply at the right-hand edge. Our GDP goes up even more steeply because the material that we use has a multiplier effect. Our increase in standard of living is somewhat greater than just multiplying these increase in inputs by 1. So all this increasing demand for materials, increasing demand for farmland to grow crops, increasing demand for forests to produce timber to use, this it means that there's less and less land potentially available for each activity. They start to conflict with each other. And the mining industry in particular is very vulnerable to this conflict because, as we say, ore is where you find it. Ore meaning the material that you can use to produce valuable minerals. In other words, you can't move an ore deposit to somewhere more convenient. It is where it is. And examples of this are that cause land conflicts are the wonderful Grand Staircase National Monument in Utah, which has oil in it, and so it's been very controversial as a result. The Pebble Mine in Alaska, which is one of the largest gold and copper deposits known, is still not in production, perhaps never will be, because it threatens the Bristol Bay salmon fishery, which is one of the most important in the world and sustains the people up there. People in the Houston suburbs don't tolerate fracking. And on a wider scale, rare earth elements, REEs, are vital for green energy, for wind power, and for solar power, and they're vital for instance, electric cars, because they're needed to produce the batteries that will run these things. But China is the only major source at the moment. And if you can't find the material you need in your own country, you have to buy it from overseas, and that affects each country's foreign policy. They have to stay friends with the places they're getting things from, no matter what their other disagreements with them are. Similarly, platinum that's used for catalysts in all kinds of industrial processes comes mainly from Russia and Zimbabwe, as does nickel, which is a vital ingredient in stainless steel. So we want to have things like parks and preserves. We also need land to have our houses on. We need forests to supply the materials for building houses, cropland for food, and range and pasture land for meat production. But for instance, meat production is much more profitable in Brazil than forest land. So the world's biggest and most vital area of tropical rainforest is rather rapidly being turned into pasture land for cattle in Brazil. And that may be much more disastrous to the climate even than the use of fossil fuels. Everybody needs parks and preserves. We couldn't live in a completely urbanized and industrialized landscape. And so if you have urban land and parks and preserves taking up 20% of the land in your country, which we do, and there happen to be mineral resources under that, you can't get at them. Where they are, as we say, sterilized. And that means, and you can't move them to this 80% that you can mine, because you just can't. So this is a major problem in some cases. This is what happened. This is what mining does to the land. This is FALUN, Sweden. Sweden was a major world power for 100 years. In fact, they had colonies in Pennsylvania and Delaware before Britain did. They were here before the settlers that you learn about in most of your history lessons. And they depended for this position of power on this mine. It produced nearly all the copper that the world used for over 100 years. But they made a big hole underground, and eventually it collapsed 200 years ago and left the mine school perilously near the edge here, and the old shaft and the workshops also in danger here. And it's ugly. People actually go down as tourists, though, to see all the wonderful minerals down here. So the other major use of major career opportunities for geologists are in cleaning up this mess. So all the phases of mineral production destroy land and water resources, mining by creating these giant holes, but also by leaving big, vast tailings dams. Tailings are the very fine-grained rock flour produced when you crush the rock to get the mineral out of it. They can be very dangerous. And spoil heaps, big piles of rock taken out of the ground. And these, to the extent that these things contain sulfide minerals, they also create acid mine drainage. They acidify all the streams draining the area. In the processing, the smelting to get the ore out of rock, or the refining to increase the value of petroleum products, lots and lots of toxic waste is produced, which ends up as Superfund sites that are cleaned up in this country. Slag heaps, giant slag heaps are produced. That's the result of the molten metal that didn't that was melted to get the metal out, and the rivers are polluted again. And in using these products, we create toxic waste when we throw away batteries and light bulbs and so on that have mercury and so forth, and cadmium and things like that in them. There's also huge landfills. It's becoming a real problem for many cities in the United States to find land that can be used as a landfill, and we pollute the streams. So all kinds of earth scientists, geoscientists, geologists, geohydrologists, geochemists, geophysicists are needed to deal with all aspects of this these problems, planning to minimize them, monitoring them as they occur, investigating any accidents that occur, and remediation of the sites afterwards. So this is where my work has taken me. The white-centered stars are where I grew up and where I started to get interested in geology in Scandinavia and in the Alps, and also where I went to college in the United States. The blue-centered stars are where I have lived. So in the Carolinas, Texas, in the middle of the Arctic Ocean for 4.5 months, in Chile, in Zambia for 6 years, in India, in Korea, in Japan, in Australia. And all those yellow stars are the places where my projects have been, which is just about everywhere in the world other than the Sahara Desert and Siberia. So I started getting interested in, when I was very young, in Snowdonia, Wales, which in the native language there, which I spoke as a very young child, is called Eryri, and North Wales is Gogledd Cymru. And this is what the scenery looks like on a foggy day. Huge cliffs, which are used by climbers to train for climbing Mount Everest. And this is a shaded relief map, and these sharp boundaries between dark and light here are knife-edge ridges left behind after the glaciers melted that covered this area until 12,000 years ago. So in the 19th century, though, this land, which is now a national park, was a huge mining area. They were mining copper here, and there's still copper to be mined. So this is the ruins of one of the old mines. And but if the copper there ever became valuable enough to mine again, it would be inaccessible because it's in the national park, and it rightfully should be, because this is very, very beautiful country. A glacial cirque is this horseshoe-shaped set of ridges left by the glaciation. Then as a Boy Scout, I went camping in the Bernese Oberland in 1959. And as part of that, we walked up this glacial valley here. And you can't see it, but I'm standing, well, this is a Google Earth picture, but the viewpoint for this Google Earth slant picture is on a glacier that overhangs the valley. So we walked along the valley, came up here and then walked across this, what was then a glacier and is now melted away. This is the old lateral moraine, the smooth area as the muck left behind as the glacier eroded away. But looking backwards as I came to this point, I saw these bands in the rock here, and then a beautiful overfold, which the Google Earth picture can't show because it's made originally from a vertical picture. So I made this sketch here of a big fold in limestone rocks. And then here's the road and the river below it. When I got home, I happened to be at a yard sale and saw this book. Arthur Holmes was the man who first dated rocks by measuring the decay of uranium to lead in them. And he wrote this wonderful book, which I carried around with me all over Europe for the rest of my youth, because that provided me with the answers to everything I was looking at. Then my first job when I was a graduate student was on Ice Station T3, which is an iceberg floating around in the Arctic Ocean up here at 8330 North, and that's where the blue and yellow star is. The yellow star is the North Pole. Here's Greenland, Alaska, Russia, Norway. So it's looking down on the North Pole. These squirrely tracks here are various ice stations that were manned at various times after 1945. And T3 is the red one. It broke off an ice shelf here in Ellesmere Island in the late 30s, drifted around once, drifted around another time, and then ended up where we were. In 1962, because of some cost-cutting measures, somebody thought it would be a great idea to use bilge oil from the icebreaker Northwind that came up to visit us. So that was in the process of establishing the world's record for furthest north by sea. So they pumped the bilge oil into 45-gallon drums on the ice station. It had water in it, which caused explosions, and our mess hall got blown up, and a couple of people got killed, and there were a lot of other issues. During the same time period, a nuclear submarine visited us, an American one, and various other incidents happened, including visits from Russian scientists. And a writer called Alistair MacLean turned this into a thriller called Ice Station Zebra. And that was turned into a movie. So if you want to get a feel for what life up in the Arctic was like, with a few bells and whistles added to it, you can see that movie or read the book. Here's our camp, and notice all the rubbish out here. Here's a workshop that we had for working on our diesel generator and so on. And in the summer, on this tabular iceberg, the surface snow melts and you get these deep channels, which make it very difficult to go very far. But notice that oil drums everywhere, just rubbish everywhere. The most people that had ever been in this camp was 8 people, and it was inhabited for maybe 20 years max, even less than that when I was there. But look at the rubbish we left behind us. And that was scientists. I mean, people historically haven't cared much about what they've done to the environment. My job up there was to navigate the station, because it drifted around all the time, but we needed to know exactly where we were because we were making maps. So this is a 12 by 12 embedded in the ice, and on top, under that cover, is a theodolite, which was a modern version of this beautiful old surveying instrument here. The telescope is for looking at the stars. The thing turns around a vertical axis here, so you can read off horizontal angles on this scale. Everything's encased in brass so that it doesn't get wet and start to mold. You can get accurate readings through this magnifying glass. There's a compass here. There's adjustment screws and levels here. So these are very beautiful instruments and very, very carefully made. And I also reported regularly to the World Meteorological Organization here in my weather huts. The sun is just setting in August, and you can see there's a wind getting up. We're going to have a blizzard, and this smooth area here is blowing ice crystals. Then I went to Central Africa. So, and there my job was to explore for copper using, by going down pits that had been dug and mapping the geology and sampling the sides of the pit and analyzing them for copper. So this pit's about 40 feet deep and about 2 foot 3 inches in diameter. And there's me beginning to go down it on a piece of wood over this pulley. And here's my when we found anything, we would tunnel between adjacent pits to make what we call them crosscuts. And here's my sampler in a crosscut, and there's he's going to cut a channel sample along there where those pegs are. Somebody digging the pit, and my sampler getting ready to go down here. But this is the mine shaft. This was a very urgent job to investigate some ore that had been left behind, and the mine shaft there is a mile deep. And now I ended up the last part of my career using sea surface oil slicks to determine whether there was oil in offshore deep water basins. I should say here that part of my training was as an oceanographer, and this was a more oceanographic project in essence, but the aim was geological. So when you have a seafloor seep, the oil comes out as droplets slowly and rises to the sea surface and forms a little pancake when it spreads out. And in the central area here, it's thicker, and because of interference, you have Newton's rings here, and so you have a very bright series of colors. In rougher water, they look like the one over here on the right, and even rougher water like the one on the left. But they spread out, these pancakes spread out very quickly to form a slick that you can see from space. So I was using satellite imagery to map these things. And why is that important? Well, there are 3 things you need to have to be able to produce oil. One is you need a structure to trap it, like this anticline. And the second one is you need a reservoir of porous rock that can hold the oil. Those things are usually investigated and discovered by use of seismic data, which is where you let off small explosions and map the reflections coming back from the deep in the earth. And here's an anticline shown in seismic data. You can also determine from the amplitudes of these waves what kind of rock you're looking at and whether it's porous or not, the amplitudes and the velocities. But the one thing that you can very rarely do is determine whether there is oil there to be found. If it were there, you could find it. You could, because you know where to drill to find the trap. But most wells have failed because there wasn't any oil. So the seep on the seafloor is the best evidence that there's oil in the system. And the easy, cheap way to find those seeps, which could be beneath 2 miles of water, was the way I did, finding the slick on the surface and mapping it on space imagery. So that was really, really important. So that's my career and my traveling and whatnot. And as I say, being a geologist is one of the best ways to see the world. It's lots of fun. But if you don't become a geologist, what could you do to help us get ready for this huge transition in lifestyle that we will need in order to preserve our civilization? Well, clearly, the first requirement is to minimize your consumption of fuels and minerals. Second one, minimize your waste, recycle. We only recycle about 30% of everything now. If we need to recycle much more, but it becomes much more expensive to recycle the more you recycle, which is a problem. Go green, use green energy, reuse things where you can rather than buy new. Go local. When you buy things that are made in China or Bangladesh or somewhere, and they're shipped all over the world to get to you. That's a huge amount of steel that gets used to build the container ships, and a huge amount of fuel used to propel them across the oceans. Minimize your footprint where you can by consuming less land. If you have your house on a lot of land, try and grow stuff or do something productive with that land. Don't take an enormous land out of circulation for or put it in unproductive use. More important, though, is where you can, if you're in a position to, look for technical breakthroughs that would make a big difference, because those first four are only going to make a small difference ultimately. They'll help. They'll help. They will help things getting much worse, prevent things getting much worse before they get better. But what we really need is enormous technical breakthroughs. If you do become a geologist or a geoscientist, then find stuff, keep civilization going, work well and work hard. If you're working in remediation, diligently work to clean up after industry by practicing hydrology or environmental geology. Do your job well. In both, no matter what field of geology you work in, be responsible for the environment in everything you do. If you run into a situation where you're being asked to do something that you know is not in the world's best interest, because somebody wants to make a whole heap of money, stand up against them. You may have to be brave. The worst thing to do is just not fight back if people are doing things you know should not be done. And finally, do and use the very, very best science. That way we can get the best bang for the buck. We can produce the things we need for our civilization with the least damage. Thank you very much. That is the end of my talk, and I'm open to questions, and there's some suggestions for further resources for the teachers. Thank you.
Thank you, John. That was really great. I appreciate it. And especially the way you ended with this call to always be aware of what is ethically correct. Geoscientists have a code of ethics, just like you think of doctors having an ethical code, and protecting the Earth's resources is part of that. So I'm glad that you highlighted that. Let me see if we have some questions. I have one for you, John, and you'd mentioned part of it, but what inspired you to become a geoscientist?
Well, the first thing, Linda, was that I lived in, North Wales is a very interesting geological place. I mean, the effects of the glaciers are obvious. So I became very interested, basically from the climate point of view. Why was the place covered with ice until 12,000 years ago? You know, and why does the ice carve the land this way? And then I went to Scandinavia, which I didn't mention, and again, everything was carved by glaciers. And then I went to the Alps, and there were these marvelous structures, these huge folds, these rocks, widely varying rocks, igneous rocks from deep in the earth that were overlying limestones. And the whole thing just fascinated me. And then too, I also had, by the time I was in high school, I also began to become very concerned about the use of resources, because it became very clear that, for instance, in Britain, we had smog. Every winter we'd have smog in London, would kill thousands of people, a smog consisting largely of coal smoke. No river in Britain was unpolluted. There were no fish if you fell in the Thames, you had to have your stomach pumped out. So I became very concerned about the way that human beings were absolutely altering the face of the earth, and I decided to do something about it.
Good. That's great. That's great. And I think there are a lot of young minds today that have that similar kind of drive to keep this work going. That's part of why we're here today, to inspire you students out there to think about what you can do to help make things better in the future. And Ms. Kapnick, if your students would like to ask a question, we'll go ahead and open the floor to you if you have a question. We'd welcome one.
Okay, we actually had two that they were wondering why y'all were talking. Did you want to ask it or you want me to? Sure.
So say we don't take care of our Earth, how much longer will the Earth last?
So he said, if we don't take care of our Earth, like now, like if we're not working on sustaining it or solving some of the problems, how long do we have left at this rate?
Well, the end will not be sudden, and in some ways, we're seeing the beginning of the end. I mean, we're seeing phenomena in the climate weather that we shouldn't expect to see. We're seeing every year is warmer than the one before. The hurricanes are getting more frequent and bigger. The ice is melting off the Arctic Ocean, and that could be a real tipping point, because when the land around the Arctic now is a desert because ice does not evaporate and form rain. So when the ice melts, the land around the Arctic will get much wetter, and it's very uncertain yet what the long-term consequences of that may be, but they may be a lot more tundra. And there's also the possibility that the world's oceanic circulation will slow down, and that would end up with causing very, very nasty cold climate in Europe, because the warming influence of the Gulf Stream would be lessened. But we're also seeing the beginning of the deterioration in other ways. We're seeing part of the cause of the Syrian conflict, for example, is the fact that there was a 3-year drought in Syria, and over 1 million people, several million people, abandoned the countryside and went to live in Damascus, and that caused pressures that the country's political system could not handle. So, and that's the way it will go. The way it will go is increasing famines, people being forced to move away from the coast because the coast is being drowned by rising sea levels, increasingly bad weather in places, and then finally, at some point, food becomes a problem. And after enough local famines, eventually you get to the point where there's a worldwide shortage of okay.
Well, they call economics a dismal science, but that's we did, it's really a call to help us in the future to continue working and approaching these problems. And part of why we're here today is to make you aware of it. And we keep hope that we'll be able to find some solutions to this. Was there another question from the class?
There was. They were wondering how, like if you were a geologist and traveling, how that would affect you having a family, and if that was hard going into that field, basically.
Yes, it can be very hard. I myself did not have a family until considerably later in life than most people, because living in Africa, medical facilities were very bad. So we didn't take that chance. And yes, some of the places you're in can be high risk, or you can be working on a drilling rig and not see your family very often. So it does make things difficult. On the other hand,
I was going to say, but besides that, it's a lot of fun.
we're much more able to handle it.
Well, I think you would also say, John, what was driving you, you mentioned the beauty of some of the places that you visited too, not just the facilities, but the natural beauty.
Yeah, you see things that very, very few other people get to see. Beautiful, wonderful mountains, deserts that stretch off into the distance. Like I've been to Western China, Xinjiang, which is another place where there are issues, political issues now as a result of climate. But that's the Silk Road area. It's beautiful. Everything is totally beautiful. And sometimes it's worth a little personal sacrifice to be able to see these things.
Well, I know our time is getting short. Thank you very much for your questions. John, would you mind, you had a couple of resources that we wanted to share, some really good things that we'll attach to the website that would allow you to look at some hands-on. We highly recommend Google Earth Pro. It's a wonderful way to explore the world using the technology. And John, if you would just kind of mention some of the other exercises you selected.
Let me show you one thing in Google Earth Pro that's not in the exercise. This is a view.
Okay.
This is a view of also. Oh, I need to share the screen.
Yes, thank you.
Wait a minute. I've got to get back so that I can see you guys. Here we go. Share screen. Here's a view, an oblique view. You can do this in Google Earth. You can rotate from a vertical view to a very shallow horizontal view. And this is downtown Austin. This is the Mexican Arts Museum here in the front, and the Congress Avenue Bridge, and the Lamar, and the First Avenue, and then the railway bridge. And this illustrates some of the things you can see with Google Earth. This is the floodplain. This is where the Long Center and the Palmer Auditorium are, and the newspaper. And it used to flood in every flood. So that's part of the floodplain of the Colorado River. But if you look on this side where Rainey Street and the eastern end of downtown are, this is higher, and you can see that. This is a terrace, a river terrace left behind as the river carved downwards. And then in the background, you can see a higher terrace beyond Barton Springs. And then on the skyline, there's the normal land surface. So you can see a lot of geology in using Google Earth. Here's the terrace that West Austin is built on here. This is old West Austin. And the Mount Bonnell Fault runs right here, is the escarpment of the Mount Bonnell Fault. So that's one thing that you can do with Google Earth that isn't on the exercise. Let me, okay.
Thank you. And I know we hope that you come back and visit our website. We'll be posting this recording as well as the presentations. You can share it with other students. For those of you watching on YouTube, if you have a question or a comment, please leave it below. We want to thank you very much, John. Thank you so much for the presentation that you've given today.
Okay.
Greatly appreciate it.
And thank you for being there, kids.
Yeah, thank you. Thank you. Keep studying. Good luck.
Yep.
We will also ask you if this will be posted on our website and on YouTube. Check the description on the video for links for more information on our website. And don't miss our next talk, which is this Thursday at 10 o'clock on Earth Date with Mark Blunt at 10 o'clock. So thank you very much. We appreciate your joining us today. Goodbye, everyone. Stay safe. Bye.
Thank you. Thank you.
Thank you. Thank you. Bye-bye.